Yeah. Okay, let's make a start for today. Good morning and welcome to E141 lecture number 5. A couple announcements first. You noticed that the website has been down for the past 24 hours or so you may not be able to print out notes for the lecture, and I made a bunch of copies. Hopefully that will be enough for everybody in the class. Should you please distribute that around. And if you checked your email recently, I also sent you lecture notes through email. So we have this class email alias that you can use to contact everybody in the class. So it's e141-class@corey.eecs. But please use this email only in emergency kind of situations, like today that the website was down, so I had to send you this over email, because you have other means for class interaction, such as news group, if you want to discuss something with your colleagues. But just be reasonable and make sure you use this email when it's really needed. Lab sessions have started yesterday, and from the feedback I got from TAs, it seems that most people struggled with account setup and getting started type of problems. So for those of you who are still not familiar with Unix environment, here's a pretty useful hint, and that is that you have to source your CSHRC to apply the changes once you make some changes to your CSHRC file, or you can log out and log back in. That's the same, has the same effect. And over here you would need to make some changes to set up the right path to be able to run Cadence software. We are rolling with homeworks on a weekly basis now. Homework number 2 is due on Thursday, and we will post homework number 3 on the same day. For homework number 2, you observe a change in problem 1b. We added this parameter 2 phi f is equal to negative 0.6 volts, so you do not ignore body effect parameter. And I have to repeat this again. Drop-off location for homeworks is 240 Corey. I've heard from people in 558 that some of you tried to turn in homework over there. So just to make sure that you turn it into right box, you will find E141 box in 240 Corey. That's the room where you go through to get into a Corey backyard, courtyard, and the second floor. Any questions about labs, homeworks, everything clear? Yes?
Before class started?
I think this homework will be due at 5 p.m. because that's how TAs gave you the deadline on the assignment. So turn it in by 5 p.m. and 2:40. And please use the news group. I've seen there is about 40 people who have joined so far, and there's been some pretty good discussion about class topics and also some general information about account setup, how do you work from home, and so on. So if you have questions, I encourage you to go to the news group. Okay, so today we are going to do a brief review of what we discussed last time and continue with MOS transistor models, and we will derive large signal models for current, and after that we will analyze inverter and derive a voltage transfer characteristic. That's also going to be helpful for your homework for this week. And then after that we're going to transition over to dynamic behavior of MOS transistor and analyze parameters such as transistor capacitances and resistances, and see how can we model transistors to be able to analyze gates from the delay and performance perspective. Okay, going back to what we discussed last time. So we introduced a concept of threshold voltage. That is, when you have MOS transistor, you apply certain voltage on your gate terminal, and there you create a depletion region under the gate. And initially for the small VGS, And then when you keep increasing that VGS, then you have more and more carriers, and this layer becomes inverted. So instead of P-type material, you get N-type material. And that creates your conductive channel. Then when you apply drain to source voltage, then you move these carriers across the channel, and that forms a current for your device. And you always calculate that current on reference to the drain terminal, ID current. So when you exceed certain value that is called a threshold, then your transistor is turned on. For small values of VDS, you first have linear mode of operation, where you have that your channel voltage at the point X is VGS exceeds VGS is equal to VGS minus VT, and in order for this transistor to be conductive, VGS has to be higher than VT, but it's also higher than this VDS plus VT. Now when you keep increasing VDS, your current will also keep increasing, and then you have a transistor in linear mode. And that happens all the way to some point where your VDS reaches some critical value that is equal to VGS minus VT, where your channel becomes pinched off at the drain side. And then you enter the saturation mode of operation, where further increases in your VDS to a first approximation can no longer yield increase in your device current. But that's not entirely true, because when you keep increasing your VDS, then this depletion region at the drain side widens, and then you have basically effectively shortening your channel length. And then due to that effect, you have more and more current as you keep increasing VDS. So you have that constant slope that we attribute to channel length modulation, that you basically modulate the length of your channel by increasing this depletion region on the drain side. And the way you identify if the transistor is in saturation is that you need to observe the relationships between voltage values at different transistor terminals. So transistor has to be obviously turned on, so VGS has to be greater than VT, and also VDS has to be greater than VGS minus VT, or equivalently VGS is less than VDS plus VT in one compact formula. So that's your transistor in saturation. That's very important mode of operation to understand. So in the past, when we had long channel transistors, we observed this good old quadratic relationship between the channel current ID and the drain to source voltage on this axis as we plot family of curves for different VGS. So what you observe in this graph is that the separation of these curves, ID versus VDS, for different VGS values gets larger and larger for the same incremental increase in your VGS. And therefore we have a quadratic relationship between ID and VGS. So now the boundary line between the two modes of operations that we analyze between resistive and saturation is this VDS is equal to VGS minus VT. That's when we kept increasing our VDS, and then at some point when the channel is pinched off, that is shown in this dotted line over here. So that's the boundary between resistive and saturation mode. So this is a summary of modes of operation that we introduced. So for VGS less than VT, we assume that the current is equal to 0, but we will get back to that in more detail when we analyze power consumption and sources of power consumption, because that's not entirely true, since transistors are really conductive in the sub-threshold regime. There is leakage current, and we'll talk about that in more detail. But for the introduction here, we are mostly interested in this resistive and saturation modes of operation. So that's what you really need to understand here to be able to analyze delay and performance of circuits. So for the resistive mode, we have transistor current that is given with this formula, and we derive that formula using the charge equation that we have, that our ID was equal to in the saturation mode we had for the linear region, so we basically derived the total amount of charge under the channel and provided this formula for the current that we have. Kn prime W over L is equal to VGS minus VT times VDS squared over 2. And then for the saturation we had ID is equal Kn prime over 2 W over L VGS minus VT squared, and then this channel length modulation parameter. And then we said this is good for the long channel transistor, these relationships. Now when we go over to the short channel model, then we have this effect of velocity saturation. And basically what this changed is that your ID short channel is equal to basically ID of a long channel times this parameter K of VD sat. And this parameter K of VD sat was equal to 1 over 1 plus VD sat over this critical field times L. So as you go towards short channels, this parameter K is less than 1, and then you have less current. So your relationship ID versus VGS is less than quadratic, so it's approximately linear, or at some factor that is between 1 and 2. Okay, going back to slides. So this is a summary of all these equations for the long channel. And then you can model a transistor using this model. You can look at your transistor as a equivalent current source that has different expressions for current depending on the regions of operation. And we identify saturation and resistive modes as the most important with this threshold parameter given with this formula here. So we basically look at the transistor as a 4-terminal device. Gate voltage controls the amount of current that you can produce with your transistor. Then the drain to source voltage controls the mode of operation. You have either linear or you have saturation mode. And then finally the bulk potential, and that's what you'll be going to be doing in your homework, modulates these characteristics. So it's going to shift them up and down depending if you do forward or reverse body bias. But this is a set of equations that you need to be really familiar with. So now, going over to the deep submicron era, we introduced this velocity saturation concept, where we basically have early saturation. So we have, for a very small VDS, we have horizontal field across the channel to reach some critical value where you have scattering effects and the carriers collide with each other, so you have basically constant speed of your carrier transports, and the speed can no longer increase, for what reason you have this early saturation and velocity saturation phenomenon. Also we observed, due to that effect, a linear relationship between VGS and ID. When you increase your VGS with some increments, 0.5 volt, then you have a linear relationship of ID versus VGS. And that is due to this carrier scattering effects. this is equal to about velocity saturation is equal to 10 to the 5 meters per second, and is approximately equal to this value for both NMOS and PMOS transistor. And we introduced this concept of critical electric field, that is the field across your channel where your carriers become velocity saturated. And for the NMOS, it's about 1 to 5 volts per micron. And we did some quick calculations last time when you have, for example, quarter micron long channel, and EC is equal to 2 volts per micron. Then you have your velocity saturation to occur at VDS of only 0.5 volts. So your transistor automatically enters velocity saturation. So that was the main difference between a long channel device and short channel device, in a sense that this short channel device, due to velocity saturation, would experience this long saturation region. So now the question for you. So let's assume we have this curve, and then the question is, why don't we use long channel device? Because it has more current. What's the reason we still, excuse me? Leakage. Other reason, space, that's a good one. Other capacitance. That's very good, yes. So we'll see that in the performance analysis, just to make sure that you understand this, is that in performance analysis we will see that also capacitance, due to increase in area, increases substantially, so that effect is actually dominant over in the long channel device. You still end up with a better performance from your short channel. So this is a comparison. You have more current from your long channel device than in the short channel, and we are comparing a device in the same technology for the same W/L ratio, except that the channel in one case is 10 microns, in another case is quarter micron channel. And then we see the difference between these curves. You have more current because of this quadratic spacing in VGS, and in this short channel we have early saturation, that's velocity saturation. So now, in order to analyze this device, it is of interest to develop some really simple models, analytical models, so that we can do some quick calculations. And the point is, in developing these models, is really to understand which parameters are the most important, and kind of develop models around those parameters, and also fit the curves in certain regions that are important for us to do the calculation, because including all the physical parameters is really getting out of hand. That's what you're going to do in SPICE. Plus, as you will see in your labs, when you do layout, you will have other effects that you don't account for. You have lots of parasitics and resistances, capacitances from wires and things that you don't include in these simple transistor models, and we'll get back to that later in the class. But anyway, the difference is more current in long channel, early saturation in short channel, that happens much sooner than this boundary for the conventional saturation region. So now, to simplify the model, we simply say that this early saturation that is clearly a function of this VGS, we say that it's just a straight line. That's a good approximation for us, because in this region of operation it is pretty much like a transition mode that you don't really care too much about. You really care about this resistive mode over here and the saturation mode. And we will make this simplistic assumption. So that's how we come up with this simplified model for ID versus VDS, where we identify 3 regions of operations. We have linear mode for a small VDS, we have saturation and velocity saturation. So if your VDS is greater than VDSat, you are automatically in velocity saturation. For smaller values of VGS, such that your VGT is less than VDSat, we have the conventional saturation mode. And the boundary between linear and saturation was this quadratic curve that we had in the previous case, that's given by this VDS is equal to VGT. And we made this assumption that VD sat is simply a constant. It's L times the critical field. So now this is a model, still the current source model for manual analysis. And this is really nice model. You should remember this model because it actually captures all modes of operation of a MOS transistor. So for VGT is less than 0, you have cutoff mode, and then for VGT greater than 0, you have unified formula for all 3 modes of operation, for your linear, for your saturation, and for your velocity saturation. And that's given in this unified formula where you have K prime W over L VGT times this W min, V min voltage. And you also include this channel length modulation, with V min is identified as a minimum of this VGS minus VT, VDS, and VD sat. So if you end up with V min being VD sat, then you have velocity saturation. If you have V min is equal to VGT, then you have conventional saturation equation, and then if V min is equal to VDS, you have linear mode of operation, and everything falls into picture quite nicely. Now the question is, as I mentioned, is that you have to take these models with a grain of salt and make sure that you extract the models that are accurate enough for the purposes that you use them. And this graph shows a simple model that is given in these blue lines, assuming this constant velocity saturation versus spice. And as we see, you will have pretty good agreement of the model in 2 regions of interest, in saturation mode and also in linear mode. Over here in this transition, you don't really care much about. And even if you end up in this region and still use your model, it's still sort of a good first estimate when you design your circuit. But it's really important to understand what are the dominant effects and what really causes your model to match well in these regions, such that when you start with your initial design and go over to simulation, if you need to change some parameter because you haven't met your design spec, you really need to know where is that discrepancy coming from, and to understand all these models such that you can apply the right decisions for your circuit. And this is what you're going to be doing in your homeworks. Homework problem number 1 asks you to plot these IV characteristics for a device and then estimate important parameters for the model. And it also asks you which parts of the characteristic are most important to be matched. And that's where you have to use the concepts that we introduced, in a sense that for example, when you estimate your threshold voltage, then you need to make sure that you pick the right points for your threshold. Where is the threshold most important? If you're given a current formula that from your model, now the question is, are you going to estimate your threshold based on the values somewhere over here, or maybe in saturation, or in linear mode, and why? And that's what you have to explain with that question. So basically you need to argue why you pick a certain point to estimate each of the parameters in the homework. And that's basically just to demonstrate that you understand what you're doing. To say you have to clearly explain the methodology for estimation of VT, of gamma, of lambda, and so on. So for example, for the lambda channel length modulation parameter, you can't estimate it from here because it's only valid in saturation mode. So that's what you're going to be doing, and you need to explain that just to make sure that you understand what you're doing. And in the textbook you will find these parameters that you'll be using pretty much for homeworks and so on. These are the 5 most important technology parameters that you need to be familiar with. So you need to understand from here that we just talked about today. You need to understand the models, number 1. And number 2, you need to be able to extract all of these parameters from the models. So just to understand where the models are coming from and how you get these parameters. That's why you have homework problem number 1 addressing that. Okay, any questions about models?
And then you gave us this formula for velocity saturated where you said ID is ID long channel times K. So that K is just a factor of 1/2. Because it's 1 over 1 plus VZ over EZ.
K is not just a factor of 1/2. It's this relationship. You have 1 over 1 plus V over ECL.
That V is not necessarily VDZ.
No, that V is VDS. So did I get it? Yeah, it should be K of VDS, not VDZ.
You said capacitance was the main reason we use short channel devices, but long channel devices have a higher current, which would charge the capacitors and discharge them faster, correct?
That's right. But when you will see, we will come to that probably next class. You will see basically that the product of equivalent resistance and the capacitance, you will have basically long channel less favorable because the capacitance and resistance will be higher in the long channel. That's one of the ways you can increase your resistance, by increasing the length. So if you have your long channel, then you basically first have your resistance of your driving gate to be higher, and capacitance of the load will be also higher due to your due to a larger area, but you will have somewhat a higher current because of the quadratic benefit, but they kind of turn out in a favor of short channel. Okay, now good. Let's use some formulas from that we just derived to understand a behavior of a MOS transistor as a switch. So let's take a look at our MOS transistor over here that is described with this ID versus VDS equations, and let's assume that we have to, for example, provide a discharge of this capacitor. Now the question is, given that this current voltage relationship is non-linear, how do you simplify a model of your transistor such that you can do still accurate and quick analysis of the performance of your circuit? So one way to do that is to model your transistor as equivalent resistance. So you basically have this model. So you have load, and then you have your resistance. But now the way you find a resistance is simply by doing this, right? By definition, so it's V over I, and then you derive that from your VDS over ID. So you have, this is your ID, and this is your VDS. So try to provide a model of this non-linear element for a simple analysis. And then when you plot a curve ID versus VDS, assuming that VGS is equal to VDD, for example, so this is the curve, VGS is equal to VDD, then what you have is that you're starting your transition over here at VDS is equal to VDD, and what you're interested to find is how long does it take to traverse this path starting from operating point at VDS is equal to VDD, go all the way down this curve to VDD over 2, because that's where you define your delay as the time it takes to get to the switching threshold. That is 50% of your signal swing. And if you look at the resistance over at this point, so the slope of this line over here, this angle, corresponds to this resistance at this point. Let's see if this is a point at time 0, this is R0. And then when you move along this curve and discharge the capacitance, then what's happening is that your resistance over here you get a new value. For each point, you get different resistance until you finally enter the linear mode where your slope is constant. So you have a couple things going on here that are not really favorable. So number one, you have that your resistance is dependent on time. It varies over time as you traverse this path from VDD to VDD over 2. Number two, this is non-linear characteristic. And the question is how you represent the behavior of a device in such a complicated relationship between your resistance and time. So now it would be good to obtain the average resistance over this period of time that we are really interested to kind of linearize it and make it a constant. So it's independent of time and it's linear. So we transform that nonlinear model. And we can do that by simply averaging resistance over a time period that takes to traverse this path. And then you have 1 over T2 minus T1 when you integrate your resistance T1, T2 R on of T dt. So that is equal to 1 over T2 minus T1 average between T1 and T2, and then you have simply VDS of T divided by ID of T times dt. So then you can solve for this expression, and then you end up with minus VDD over 2 when you integrate between VDD and VDD over 2, and then you have voltage divided by ID sat 1 plus lambda times V dV. So now in order to obtain the resistance, you need to make an assumption about the mode of operation so that you can choose the appropriate model. And in general, when you make these kind of assumptions, it's always good to make an assumption and then carry it all the way through, get a solution, and then plug the numbers back in to check if your assumption is valid, to make sure that you apply the correct model. And if not, then if that method breaks, you probably need to make a different assumption at some point. But it is valid to assume that over here the channel is, the transistor is in velocity saturation. And when you solve this integral and do little approximation, then you have 3/4 VDD over ID sat 1 minus 7 over 9 lambda times VDD. Okay, question?
Slides it's 5 or 6.
Okay, we'll get to that. Okay. Okay, so this is one way to estimate equivalent resistance, but you see it's pretty tedious work to kind of solve these integrals and do a lot of averaging and so on. So now let's say we can do it even simpler. We can just simply say that our equivalent resistance, now new strategy. So now our equivalent resistance is between these 2 points. So you have R naught, and then you have another line here that is your R midpoint. So this is VDD over 2. I can now say that my resistance is simply average of the 2 endpoints. And this assumption is valid in case that resistance doesn't experience highly non-linear behavior between these 2 points. So if it's reasonably linear, then this assumption is really good, and it will save you a lot of headaches and vigorous math exercise. So you will then basically just have that your R equivalent is equal to 1/2 of, so your R naught would be, your VDS is equal to VDD, and then you have ID set 1 plus lambda times VDD, plus this other point is VDD over 2, ID set 1 plus lambda VDD. And then you follow this, do some algebraic transformations over here, and you need to do some Taylor expansion, and then you will get that you need to assume that basically lambda VDD is much less than 1, so that the factors type of 1 plus lambda VDD can be approximated as 1 minus lambda VDD plus higher order terms that you neglect, and then you end up with the formula 3/4 VDD over ID set 1 minus 5/6 times lambda VDD. And in the previous calculation, where we had to solve that integral and average out of the entire interval, we had, instead of this 5/6, we had 7/9. So difference between 5/6 and 7/9 is not that much, right? Especially that you have 1 minus that factor times lambda VDD, which is fairly small. So that gives you a really good approximation. And this is kind of strategy that you would want to go after every time you have some problem. You try to find analytical model that is simple enough, you understand where the model is coming from, make sure that you are making reasonable assumptions, and you will likely end up with a very good design. Okay, questions? So let's go back to slides. Thank you. So that's the basic methodology. You start from IV characteristics, you average out resistance, say that's too complicated, find a better and simpler model that is still accurate enough, and then you're good. So you have your equivalent resistance of a transistor that you can use for the delay analysis that we will do in the next class. And you simply model transistor as a switch. For VGS greater than VT, you have this equivalent resistance. For VGS less than VT, it's open circuit. So now here's a plot of equivalent resistance that we saw last time, that plots equivalent resistance in ohms for a transistor of W over L is equal to 1 and minimum channel length 1/4 micron. And you see that as you decrease your VDS, that your resistance first stays fairly constant and fairly linear in VDS, and then when you reach some point where you are going to turn off your transistor at around 0.5 volts, then your resistance increases by a large amount as you go traverse through the from the saturation, going down that curve where you go into linear mode and then finally cut off. These are some of the values for NMOS and PMOS for the technology that we use in the class, and what you should remember from this table is just basically the order of magnitude and kind of values that you may expect in practice when designing circuits in this technology. So it's about kilo ohm, tens of kilo ohms value that is pretty low resistance that's considered a good driver. For values of W larger than this ratio, you have to scale this equivalent resistance by that amount. So you have longer channel, higher resistance, or wider channel, you have lower resistance. So by making your transistor wider, your equivalent resistance is smaller. And this makes sense because when you make your transistor wider, then you have more drive capability. Therefore, you will discharge your capacitances quicker. And you just use that kind of intuition to make sure that you understand what's going on. Okay, so now that we have the current relationships and that we understand the resistive model of a transistor, now we can go back to our voltage transfer characteristics and see how we can derive parameters on VTC. It's instructive to start with an inverter example because it is single most important gate in CMOS, and principles derived for an inverter will be applicable to more complex gates and more complex blocks such as multipliers, microprocessors, and so on. So now let's take a look at this inverter, and this is a physical representation of an inverter. That's what you're going to be doing in labs this week. So you have common polysilicon that defines the gate electrodes, and then you have a PMOS on top and an NMOS on the bottom, and you have their drains connected to each other through this metal one. So now this is a first order model of this inverter. So it's basically a very simple switch model. Over here on the left hand side, you assume that when your input is equal to logic 1, that is VDD, then your PMOS is turned off. And then you simply have this low resistive path to ground through the equivalent resistance of NMOS. And then your V out will be equal to 0 after some period of time when the transients settle. Similarly, when V in is equal to 0, then NMOS is turned off, and PMOS is turned on, and then you have steady state at V out is equal to VDD, that is your VOH. So now in DC regime, your switching threshold is very important as well, and that is a function of the relative drive capability of NMOS and PMOS, and that's what we are going to do next. Using the current expressions that we derived, we are going to see how we can apply them to derive the VTC of an inverter, and then we can carry on that analysis for more complicated gates. But before we do that, let's analyze some of the properties of the CMOS inverter and sort of derive some characteristics for the CMOS logic gates that we will be analyzing in the upcoming lectures. So first, and a very important property, is that it has a full rail-to-rail swing. So you basically have either PMOS is turned on or NMOS is turned on, in which case in DC condition you have VOH is equal to VDD or VOL is equal to 0. So you have clearly defined logic levels at 0 and VDD. You notice that in steady state, logic levels are independent on transistor size. And no matter how strong is your transistor, after all the transients settle, you will have basically one of the transistors that's pulling down or pulling up while the other is turned off. And there you will have clearly defined logic 0 and logic 1. And this type of logic circuits where logic levels are independent on transistor size is called ratio-less logic. You will see later on there is logic families where basically your voltage levels are defined by the relative strength of transistors, and then you will have ratio of the equivalent resistances to define logic levels, which we will call ratioed logic. Very important property is that it has low output resistance. As we saw from the table, it's in the kilo ohm range. That's what you need to remember. And what this does is basically makes it really immune to noise sources, because it provides a good solid voltage, as we discussed last week. That's very important property when you have large noise margins. It has very high input resistance. It's also very important because what that means is that it doesn't load much the previous gate, except in transient regime where there is a lot of capacitive loading. But in DC condition, it's basically just you will have your gate that's connected to the output of the previous gate, and the current to the gate is negligible in DC, almost zero. So you have basically very little loading and still clearly defined DC levels. And if you ignore leakage, there is no direct path current in steady state. You have either 0 or 1, and no current in steady state. Unlike, for example, ratioed logic that will have to provide a voltage level depending on the ratio of two transistors that are active, in which case they will have to dissipate some static current. But these are just some of the properties that we will get back to in analysis of more complicated logic gates in full static CMOS implementation. Yes?
Question number 2. Why the CMOS inverter is ratio-less logic? The rest depends on PMOS and MOS with P strong N or N strong N.
The question is why is a CMOS inverter ratio-less logic? Because the threshold depends on switching threshold. You say it depends on PMOS and NMOS. As we say, this is a DC property. So you basically analyze your circuit when it's all the transients are settled. When your PMOS is fully turned off and NMOS is turned on, or when your NMOS is turned off and PMOS is turned on. So you define just your DC levels, and in that case you basically have a voltage level that doesn't depend on the size of your transistor. For example, if you have a minimum sized transistor for the NMOS and 2 times a larger PMOS, then you have logic level of 1 is equal to VDD, logic level of 0 is equal to 0. And then when you increase the size of either PMOS or NMOS, then you still have the same logic levels. It really doesn't depend on the absolute size of the device. It's not about threshold. Okay, so now let's go back to the VTC, voltage transfer characteristic business, and analyze a CMOS inverter. If you go to the overhead, please, thank you. So we analyze the following case. So this is our good CMOS inverter, and what we want to plot eventually is voltage transfer characteristics. So this is the final goal. So you have VTC, you have V in, and then you have V out. You want to be able to derive this curve, okay? So in order to do so, and now what do we know about this gate? We know current voltage relationships for NMOS, and we know current voltage relationships for PMOS. And we are going to combine them together to be able to derive this voltage transfer characteristic. In order to do so, we first need to get some conventions here. So let's assume that we work in a coordinate system of this guy here, NMOS. So then we have clearly that for the NMOS, we have simply that VDS is equal to V out, and VGS is equal to V in. Now for the PMOS, we have VDSP, this is VDSN and VGSN. VDSP is equal to V out minus VDD, and we have VGSP is equal to V in minus VDD. Okay? But that's not what we have. So what we have for the PMOS, we have IDP, and IDP is the current that goes, let me do another pen here, it's not good. We have IDP that goes like that, and we have IDN over here. Okay, so we have for the PMOS, we have VDSP. So basically all the values are negative. So you have VGSP is equal -1, -1.5, -2, and so on. So now we have to translate this I versus VD relationship into this coordinate system of the NMOS. So then we need to apply some transformations. So first of all, we have, in terms of IDN, is equal to negative IDP. So it's relationship number 1. Then we also have that our VGSP is equal to V in minus VDD. And finally, for the VDS, we have that VDSP is equal to V out minus VDD. So what we are going to do now is we are going to plot ID versus VDS for NMOS, and then we will going to superimpose IV characteristics of the PMOS on top of that NMOS family of curves. And the family of curves for the PMOS in this case are called load lines, because we analyze NMOS as the main device and PMOS as the load device. So what this first relationship tells us is that basically to get ID in IDP in the IDN coordinate system, all we need to do is to flip a sign. So you basically have to take these curves and flip them over. Okay? And then we have this VDSP is equal to V out minus VDD. So what you need to have over there in terms of V out, that is equal to VDSP plus VDD. So what you need to do is basically first flip this curve to change the sign, and then shift it over by VDD using this relationship over here. And then what you end up with, you basically have load lines for NMOS. So you have IDN versus V out. And now VGS for the NMOS is equal to V in, right? So you have V in is equal to 0.5, we have V in is equal to 1, V in is equal to 1.5, V in is equal to 2. Okay? And now for the PMOS, we have VDD over here. And then for the PMOS, you have basically flipped over and translated on the voltage. You have the same curve for V in is equal to 0.5. Then you have V in is equal to 1, V in is equal to 1.5, V in is equal to 2. And now, important relationship is that your IDN must be equal to negative IDP. So for each V in and V out pair. So what you're basically doing now is that you start from this point, and then for a given V in, you assume that you have to find intersection between your NMOS and PMOS curves for the same V in. So you basically go, if your NMOS is equal to, let's see, your NMOS is V in is equal to 0.5, then you have to intersect with your PMOS over here. So then you have NMOS is equal to 1, your PMOS is over here. So I think I didn't draw this well, so we'll go back to slides. Oh, actually this is reversed. Yeah, thank you. So this is actually, we didn't apply the coordinate transform over here. So basically we have that for the PMOS, we have VGSP is equal to V in minus VDD, thank you. And then we have basically over here, if VDD is equal to 2.5, then we have V in is equal to 0, then V in is equal to 0.5, then we have V in is equal to 1, 1.5, and V in is equal to 2 over here. Okay, now it makes sense. So we take then V in is equal to 0.5, we end up here. So that's point number 1. Then we have V in is equal to 1, we move over here to point number 2. V in is equal to 1.5, then we are already here. And then we have V in is equal to 2, then we are over here. And if we started, this is 0, and this is 5. And now using these values, we can plot voltage transfer characteristic.
Can you write bigger?
Bigger font? Okay, yes, sure. Okay, let me then highlight important points here. So step number 1, you have this ID versus V out family of curves for NMOS. Then you have to transfer PMOS load lines into a coordinate system of this NMOS device. So you have to do 3 things. You have to flip over the sign for the PMOS current, then you have to shift it over for the VDS over here, and then you have to sort of flip the labeling on VGS, because you have that this relationship that V in is equal to VGSP plus VDD. Okay. So now let's go back to slides for a moment. So this is what we've been doing here, basically, just applying this coordinate transform here. So we have flip the curves, then we have shift them over, and also reverse the labeling on VGS. And that's how you end up with this CMOS inverter load characteristics. So you start from here, V in is equal to 0, then you move over to this point, then you move over here, V in equal to 1. So you see that for this initial case, when you start off from V in equal to 0, you make very little progress on the V out axis. And then going over here from 1 to 1.5, you jump over a huge step on V out. So that's basically the region where both of your transistors are in saturation and have you a lot of gain. And then you will end up basically going from logic 1 over here to logic 0, and that's where you settle eventually for Vin is equal to 2.5. When you put all these together, you basically start from this point where your NMOS transistor is turned off, your PMOS is in resistive mode. Then you go down the curve, and your NMOS basically is now becoming saturated, enters the saturation mode. PMOS is still resistive. And then finally both transistors enter saturation mode, very high gain region, and you quickly jump over it. You have your NMOS in resistive mode, PMOS in saturation, and finally you as you further increase V in, you fully turn off your PMOS and you have NMOS in resistive mode. Okay? Is this clear for everybody? And when you plot this VTC, you basically have to equate currents, and you need to make sure that you verify the mode of operation for both of your devices. Make an assumption, carry the derivation through, and do it again. So now, very important parameter for this voltage transfer characteristic is exactly this switching threshold. And it is very important to be able to analyze this curve and calculate this intersection point. So what are the important assumptions that we need to make in order to calculate the switching threshold? So basically, by definition, Vm is found at the point where input and output are equal, right? So that means that VDS is equal to VGS. Since VDS is equal to VGS, what is this mode of operation? Velocity saturation, that's right. So now we can further assume that our VD sat is less than Vm minus Vt. So that's basically still in velocity saturation at halfway between 0 and VDD. And this is pretty valid assumption, because if you recall the numbers that we quoted, that velocity saturation happens at about 0.5 volts or so. This is 1.25, so that's still a good assumption. So for the first order analysis, we can ignore channel length modulation. And all we need to do now is basically make currents equal. So we have Kn times Vd sat n times Vm minus Vtn minus Vd sat n divided by 2 plus Kp times Vd sat p times Vm minus Vtp minus Vdd minus Vd sat p over 2, that's equal to 0. This is negative here. A little bigger? Okay. So let me write this. So you basically have ID sat n plus ID sat p is equal to 0. Is this legible? Good enough font? Okay, good. So now when you plug in the values for ID sat n and ID sat p and solve for this expression, then you have that your switching threshold Vm is equal to Vtn plus Vd sat n over 2 plus factor r Vdd plus Vtp. Vtp is negative here, and so is Vd sat p. One plus r, where this r parameter is equal to Kp times Vd sat p divided by Kn VD sat n. So that's the formula for switching threshold. Now the question is, how do you control this switching threshold? What does it depend on? So basically, when you look at this expression, you pretty much have that your process parameters are present here. VTN, this is a property of your NMOS, that's a constant that's given to you. Then PMOS, VD set is constant, threshold is constant, VDD is constant. So basically, this parameter R is what can shift your threshold left and right, and that depends on the ratio of these conductivities in this two devices, where you have that your K parameter is, let's see if this is, yeah, so you have it from here. So it's basically determined by the ratio of Kp and Kn. Yeah. Those currents are in, let's see, I guess we are missing here a term, right? No, this is saturation, right? This is saturation, because you have VD sat n times this, right? So you have basically, this is your, over here you have VGT times VD sat minus VD sat square over 2, right? And then you have this Kn, and I guess we need W over L over here. W over L and W over LP. Let me write this down again because it's getting messy. So we have basically Kn W over Ln times VD sat n Vm minus Vt n minus VD sat n over 2 plus Kp W over Lp VD sat p times Vm minus Vtp minus VDD minus VD sat p over 2 is equal to 0. Question?
You assume that VD sat is less than Vm minus V threshold. Is that true for the PMOS? I mean, using the parameters that you gave us on page 103, they don't seem to be right. That's
excellent observation. So that's basically you make an assumption, carry it through, and then go back and check your assumption. So in this case, PMOS will be in saturation and NMOS will be velocity saturated, if you want to do it precisely. But it's excellent point. Everybody understand the question? So basically, we made an assumption here that VD sat is less than Vm minus Vt, right? So we have to make that assumption and say, okay, let's assume it's reasonable to assume that transistors are in velocity saturation, but since we have this parameter Vm that we need to calculate, we still don't know if that assumption is valid or not, right? So you need to carry through this analysis and then see if really your VD sat for NMOS and PMOS satisfy this formula. If the answer is yes, then your initial assumption was good. If the answer is no, then you have to revise your assumption and basically put velocity saturation equation for NMOS and put classical saturation equation for PMOS, and then work through the analysis again and then again, just the last step is double check if that's correct or not. Okay? Question?
On the homework, when you asked us to look for like the VM, the VOH, and VOL, are we supposed to assume velocity saturation? What's the value for it? Or are we supposed to look at the value? Or?
You can you use this what's that problem number? Problem 2. Let's see, what does the homework say? Ignore velocity saturation? Yeah. Yeah. Thanks, Lynn. Yeah. Yeah, ignore velocity saturation. Okay. So it's basically just to first figure out the methodology, and then when you get comfortable later on, you can put more complicated effects. But what's interesting here is that it's interesting to derive this W over L ratio in terms of switching threshold. So you have Kn prime times Vd sat n times Vm minus Vtn minus Vd sat n over 2, and then you have Kp prime times Vd sat p times Vdd minus Vm plus Vdp plus Vd sat p over 2. And then you can calculate the ratio of W over Wp over Wn, assuming that they're equal length, for symmetric voltage transfer characteristic. And then let's plug in some numbers over here. So we have that Wp over Wn is equal to Kn is 115. This is negative 30 times Vd sat n is 0.63. This is negative 1 times we have Vm is 1.25 minus 0.43 minus 0.63 over 2, and you get these numbers from the table in the book. And then you have 1.25, it's Vdd minus Vm. Vtp is negative, so it's negative 0.4, and this is negative 1 over 2, and then you end up 3.5 for symmetric characteristic. That's a huge number, right? But luckily, what you get is that if you go back to slides, you get basically to work this formula that we just did, and you plot Vm as a function of Wp over Wn. And if you plot Wp over Wn on a logarithmic scale, then we see that basically when Wp over Wn change, let's say from over here 2 to 3, then Vm doesn't change much. And that's a good news, basically, is that your VTC characteristics doesn't shift much if you put 3.5 W over PW over N, or you put 2.5 or even 2. And I think you have numbers in the book for that, that it basically, let's see if I have it over here. So basically for 3 you have, so Wp over Wn, and this is your Vm. So for ratio of 3 you have 1.22 volts, 2.5 it's 1.18, and 2 it's 1.13. Okay. Let me see over here. Okay, so now we need to determine VIH and VIL, and in order to do so we have to basically so now we know how to determine VM, right? And to be able to determine VIH and VIL, we can simply use this piecewise linear approach that greatly simplifies our analysis. So first of all, we know that VOH and VOL in static CMOS are VDD and 0. So that's information number one. Piece of information number two is that we know this switching threshold, how to calculate. And then we can simply use this PWL approximation to compute VIL, that is equal over here to VM plus VDD minus VM divided by the gain. Right? And this is plus here because the gain is negative, right? That's V out versus V in, so it's the slope of this curve. And then in a similar way, you have VIH, so that's basically starting from this point, you have VM, and then you have this distance over here, VM divided by gain. So it's VM minus VM over G. And then you can calculate your noise margins. For high is VDD minus this VIH, for L is this VIL. So now what can we see from these expressions? So obviously it is very important to have as high gain as possible, such that this transition region is very sharp, and therefore you have maximum noise margins, because in that way, if you have a very high gain, then in limit case, when gain goes to infinity, your VIH and VIL will converge to VM. And what's good about this model is that it gives you a fairly good starting point approximation for the voltage transfer characteristic. You can work through some examples in the book that you can use this method to calculate your VIH and VIL, and you will see a fairly good agreement between the this simple analytical model and the simulated characteristic. And the simulated VTC is shown here, and you can then simply derive VIH and VIL and then compare it with the previous result. So now this is interesting slide. So this shows inverter gain when versus the input voltage. And then you can see that clearly in this transition region we have very high gain, right? And the gain is about 17 in this particular case. What's interesting about this is that basically you see that digital circuit operation is at either Vin is equal to 0 or Vin is equal to VDD. That's where we define our logic levels. That's where we want our gates to operate. And analog designers would like their gates to be exactly in this region. So it's kind of like you are either analog or digital designer if you look from this curve over here. So you have digital, a little bit of analog region, and then again you go to digital levels. But it's important to have a very high gain. So now the question is, what happens when we scale the supply voltage? And if my voltage transfer characteristic was really good and nice, like in the red curve, what is going to happen if I keep reducing my VDD? Because that's a good method for improving power consumption, as we will see in the next lecture or next week. And then you will see that if you apply 1.5 volt VDD, your VTC is still good. If you go even further down, let's say 0.5 volts, how about 0.5 volts? 0.5 volts is good enough to turn on a transistor, because you have a threshold of 0.4 for the PMOS, 0.43 for the NMOS, so it can still work. And as you notice over here is actually that this characteristic looks even nicer. It's sharper. It has a clearly defined transition in a form of this very high gain region. So now the question is, do you know why you have a shape like this compared to the high VDD? What happens here when you keep scaling your supply voltage? Are you still in velocity saturation? Or you are in regular saturation mode? You are in regular, that's right. So when you're in regular saturation mode, you have more current, you have more gain, and then your curve looks nicer. So now the question is, if my curves look really nice, why don't I always use low voltage operation, right? Sub-threshold, that's one reason. Other reasons? What's the most important reason? Why you don't want to go this low? Performance? That's right, performance. You lose in performance, so you don't want to have really low voltage because you lose in performance. What else is going on from what we've learned so far? How about noise margins? Noise margins decrease with VDD. What that causes is that you basically are no longer immune to external noise sources as much as you were for high VDD, because your external noise sources do not scale with supply voltage, so you get hurt in that case. And you can still keep decreasing voltage below the threshold when you have the sub-threshold operation, but you soon hit this fundamental limit of about it happens between like maybe 50 to 100 millivolts, when you have basically this thermal noise that starts to matter, when you have that KT on Q noise, which is basically dependent on your temperature, and that's about 26 millivolts. So the good rule of thumb is that you have about 2 to 4 VT, the thermal voltage, KT on Q, for limit to supply voltage scaling. And I think that's where I'm going to end today, and the next time we will continue with capacitances and performance analysis. See you on Thursday.